Okay, and this shows the overview of the structural intervention you can see here. And for example, this shows the strength of horizontal strength at roof of the reception building. Such stainless brace was introduced to strengthen the horizontal rigidity of the roof in a reception building. Also, we used the installed stainless band at the joint of penetrating beam, okay, connection between column and beam. And additional timber beam members were installed to at the base of the floor of the building, you can see here. And also, we introduced the strength members at the corners of the roof. You can see here stainless members installed. Finally, this is the shows the completion of the restoration project after restoration. You can see here. Okay, and I would like to conclude with the first topic of the six family house. Respecting that the structure has survived against the large earthquake since it was constructed, we conducted the minimum structural intervention successfully. And it was considered that the strongest earthquake the house experienced in history was the Great Kanto earthquake in 1923. And we simulated the seismic behavior of the building during the Kanto earthquake, Great Kanto earthquake. The analysis demonstrated that the structure survived during the earthquake, indicating the analysis method was applicable to the seismic safety evaluation of the during of the building after restoration. So I move to the next topic of the architectural structure survey for conservation of groups of traditional wood houses in South Nias, Indonesia. This project was conducted at the international collaborative study with Gajah Mada University in Indonesia. So in Indonesia is the seismic countries, and the South Nias Island are located here, and in the offshore of the Sumatra Island, Indian Ocean side, you can see here. And the Baumato village, our survey area, village. In this village, traditional houses and as you can see around traditional wood house, there are 124 traditional wood houses existing. Okay, you can see here typical structure of the traditional house: elevated floor and the roof, elevated floor and the roof, and the middle part is the living floor. Okay. This is the Obosebua and the village chief's house. Okay. And this is the ordinary people houses along the street of the Baumotaro. This is the Omosebua, the house of this village chief. And Omosebua, Omohada is the right-hand side, the Omohada, the original houses. So you can see the very large diameter wood post was used for the columns, vertical columns, and the braces. The diameter of the columns is as large as 15 centimeter or 16 centimeter. Okay. And major earthquake occurred near the Sumatra. You remember in 2004, magnitude 9.1 Sumatra earthquake was caused, and great tsunami, so the suffered. The great tsunami caused the very severe damage to the structures, not only structure, but also the a number of people were killed by the great tsunami in this by this earthquake. Nias Island is near the epicenter of this earthquake, and in 2005, after shock was caused, and the Nias earthquake was caused. You can see here. But most of the timber traditional house survived against such those big earthquake, large earthquake, and but brick masonry houses were severe damaged by this earthquake. So that means this experience meant the traditional wooden houses have the inherent potentiality against the earthquake. And so we conducted the mechanical material test of the wood were used for the construction of the traditional wooden houses. Okay. And we also conducted the inspection of the deterioration. You can see here, in such tropical climate area, termite. So aging of deterioration and harms by termite was observed, and those deterioration would reduce earthquake resistance capacity. We conducted also the microlateral measurement of those heritage structures, Omosebua and Omohada, so to know the dynamic, fundamental characteristic, natural frequency, damping factor, and vibration mode. So this show the vibration mode and vibration natural frequency of the vibration. Okay, Omosebua. But so this layer and the opening, so the large displacement was found, and the irregular caused the irregular deformation. So one of the weak point of this structure you can see here, and also we conducted manpower excitation test of Omohada. So ordinary houses, so mantle exciting one of the house, and another neighboring house is also was caused vibration was caused by this by man excitation. So house so number 4 started to vibrate with natural frequency. You can see here, and we also conducted this such vibration analysis, dynamic vibration analysis of this almost harder. So coupling effect was caused between such houses, which reduce the seismic response to the earthquake. Okay. We also conducted the seismic response analysis of almost several, and this showed the deformation during the earthquake by JMA Kobe earthquake and Hachinohe earthquake in Japan, strong ground motions. So those figures indicated the structure survived against the such Kobe earthquake and Hachinohe earthquake, big earthquake. Okay. And also we conducted the measurement of temperature and humidity in roof. Okay. As you can see here, the roof material, 2 kinds of roof material was used. One is the such roof, sangoyashi, sango leaf roof, and another is the GI sheet, metal roof. So recently in this village, such GI sheet, metal roof was used in place of the traditional sango leaf such roof. So we installed the temperature meter and humidity meter in this inside of the house, and so this showed the variation of temperature and humidity inside of the roof. Upper one shows the humidity, and the lower one shows the temperature. So variation in the roof structure of the GI sheet was larger than that of some leaf roof. This means the for the materials, roof materials, wood materials, sangoyashi leaf, traditional materials would be better for protection against the deterioration. So, but recently, for very so traditional sangoyashi roof was replaced by the new material, new GI sheet material. But those replacement would cause the materials, wood materials, more deterioration. So I will conclude the second topic. Mechanical test of the wood revealed the fundamental mechanical properties. Damage due to deterioration and harms by termite would reduce earthquake resistance capacity. Fundamental dynamic characteristic of the traditional wood house were evaluated. It was suggested that the connection between houses called dynamic coupling effect, which reduces seismic response. Earthquake response analysis indicated seismic resistance capacity. Changing the roof material from the traditional stone leaf to the modern GI sheet would promote the deterioration of the timber of the structure. Thank you for your attention.